Okay, suppose we have a curve given by a polar equation r of theta. So when we have a given angle theta, r of theta, this function of theta, tells us how far and in what direction we go from the origin to get to a point on the curve. So that this r of theta arrow, as we go from theta equals 0, say up to theta equals 2 pi or even a little beyond, the tip of the vector follows this curve, and of course the vector starts at the origin, again, follows the curve. Okay, well, a couple of things we want to be able to determine. So let's say that we have a small increment of theta, a delta theta, and a value of theta. So the value of theta tells us where our r of theta point is, and of course then the coordinates of this point here will be theta and r of theta. Okay, well then, what are the coordinates of this point going to be? Well, I want you to pause the video, because when we did this in class, we took a whole hour to work through all this because I was allowing the students who were there, and a couple of students did miss, for some pretty valid reasons. You know, I have people think through so they can answer these questions as they go. So my first question is, well, what's the coordinate of this point? This angle's theta, this is delta theta. This point is clearly theta r of theta in polar coordinates. Okay? What are the coordinates of this point? Okay, well, you should pause the video and get that. And you should have already done it. If you haven't, please do so. But I'm going to say now. Well, this angle is going to be theta plus delta theta. And r be evaluated at whatever the angle is, in which case theta plus delta theta. It's r of theta plus delta theta. Okay, that would be this point. Now these are polar coordinates. Okay, that's understood. So I'm not going to keep repeating that. But you don't want to think of these as rectangular coordinates. Okay. Now my question is, well, there are two questions. How long is this segment? Or, to a good approximation, if we assume delta theta is small, okay? I'll say the length of the now it's green. Also the area of the triangle. Okay, triangle, of course, being this triangle. Okay, so we're going to try to get to that, to some good approximation, some approximation that becomes exact as theta approaches 0. Because then we're going to be able to get expressions that we integrate to get the total arc length and to get the area, total area, between, let's say, the axes and the curve, okay? Or between two values of theta, the area of the, if we wanted the area of the segment between, let's say, here and here, if we know these angles, we want something we can integrate from this angle to this angle in order to get this area. That's our goal. Now, this goes back to, well, we encounter the fact that people don't learn to set up integrals very well in their first year calculus. They learn it long enough to pass it on a test, and maybe if they have a very solid final, they learn it to do the final, but then they pretty much forget it because it hasn't been reinforced enough. Well, this is calculus 3, and here's where we reinforce it all and learn it well enough that it's going to be easier later to reinforce. Okay, so I'll observe, well, what are the legs of this triangle? What are these two legs of the triangle? Okay? What's this length of this leg and the length of this leg? You want to stop and think about that. But here's a copy of the triangle. So hopefully you've stopped and thought about it. But the lengths of the legs are the values of r. Remember, the value of r is your displacement from here to here, or your displacement from here to here. R of theta is this. R of theta plus delta theta is this. So we have two sides of this triangle. And we've got the angle theta down here. So we've got two sides in an angle, but is that enough? Okay, well, it is kind of enough to, solve the triangle using the law of cosines. We can find the length of this, but we don't want to go to that. We want to do a pretty obvious approximation rather than pulling out some of our trigonometry, okay? So, we do this. Okay, let's go to this picture. This is a circle of radius r. How long is this side? Okay, now, you've got a delta theta here. This distance is r. This distance is r. How long is the side that connects this to this? Well, the length of the side that connects this to this, if theta is small enough, is very close to the length of the arc. And how long is the arc? Well, the arc has a length that's in proportional to the circumference of the circle, same way delta theta is to the angle all the way around the circle. Now remember, we're doing calculus here. We're not using degrees for the angles. We're using radians. The radian measure of an angle all the way around the circle is 2 pi. Is 2 pi. Okay, and the circumference of the circle is 2 pi r. Well, this means that delta theta is in the same proportion to 2 pi as the arc distance is 2 pi r. Which means that the arc distance, which is indicated by this expression here, comes right out of this. Okay? So that the third side is approximately equal to the arc distance, because the arc is almost a straight line if you have a very small delta theta. And of course the arc distance from the proportionality is 2 pi r, distance around the whole thing, times delta theta over 2 pi, which is the fraction of the arc that's contained here, okay, contained between these two angles. So we've got this. We know how far this is. Now, what does that have to do with this picture? Well, I've got to look and see what my next question was. Okay, yeah, all we're doing is the area. So, how does this help us get a good approximation to the area of this triangle? Just thinking ahead to the arc length, which is going to be a little different. Okay, so you should pause. How does this help us get a good approximation to this? Well, again, assuming you've paused, I'm going to go on. And I'm going to tell you that if r is differentiable, then r of theta plus delta theta and r of theta don't differ by much, provided delta theta is small. Now, what's it mean for the function to be differentiable? It means that the limit of the difference of these two approaches, well, the limit of the difference of these two divided by the change in the angle, which is that's going to approach the derivative, okay? And it follows, Okay, that approaches a constant number, which means that if delta theta is small, these two can't differ by much. So think about how the definition of differentiability, the definition of the derivative, ensures that the function differentiable, these two don't differ by much. Now, if the function's not continuous, it's not differentiable. So these two could differ by quite a bit if the function isn't continuous. But if it's continuous, it follows that these two don't differ by much. And I could write out all the symbols and everything, but I don't want to confuse the issue. Right now, understanding this and then going back and thinking about what the definition of the derivative, the definition of differentiability mean, ensures this. Intuitively, we know if delta theta is very small, then these two are going to be close. To make a smaller delta theta, there's going to be a smaller difference between the length of this side and the length of this side. That implies, then, that as delta theta approaches 0, what kind of a triangle does this approach? Okay, and how does that help you get the area? You should really ponder this. You should stop and ponder. But we're going to move on and say, okay, well, the area of this triangle is then going to be close to the area of this triangle. Okay? This triangle has r of theta here and r of theta here. Or maybe an r of theta bar, some theta between, some angle between theta and theta plus delta theta. If you remember setting up Riemann sums and so forth and approaching integrals, you'll understand what I mean by a sample point. Okay. So if you don't, you really need to review that. This is something you really need to understand at this point. Or are really going to need to understand as we go through integration in 3 dimensions. Okay, well, area of the triangle, the area of this triangle is close to the area of this triangle if theta is small enough. What kind of triangle is this? Well, it's nearly a right triangle because this side and this side are the same, meaning it's an isosceles triangle. These angles are therefore the same, and this angle is really small. So you got 3 angles that add up to 180 degrees. 2 of them are equal, 1 of them is tiny. That means these 2 angles are close to 90 degrees. So now we can say that, first of all, this is the length of this side is r of theta delta theta, because what we said here, okay, this proportionality, again, a picture that you really need to understand rather than just memorizing equations you're going to forget. You're not going to forget the reasoning and the picture if you really understand it. So we have our, excuse me, side here, r of theta delta theta. These are approximate right angles. So what's the area of this triangle? The approximate area, the area that's going to get more and more accurate as delta theta approaches 0. Well, area of a triangle is 1/2 the base times the altitude, and altitude is perpendicular to the base. So if this is the base, this is almost a right angle, so this is almost perpendicular to the base. As delta theta approaches 0, this does approach perpendicular. So the area is approximately 1/2 r squared of theta times delta theta. 1/2 the base r times the altitude r delta theta gives us 1/2 r squared delta theta. Okay? So the area is approximately this, and again in the sense that as we let a delta theta approach 0, this approximation becomes exact. Now, there are things I'm not writing down about that. They make this totally rigorous. There are a lot of things that have to be written down, and hopefully you understand what they are if you review again your chapter on what the integral means in Calculus 1, Calculus 2. Okay. Now, another thing is, one student said, well, that's going to be the hypotenuse times the sine of theta. And that's true, the hypotenuse is r of theta, approximately. And if you multiply that by the sine of theta, you get r of theta sine of theta. Not sine of delta theta, sorry. R of theta times the sine of the angle here, which is delta theta. So why do you get r of theta delta theta and not r of theta times the sine of delta theta? Well, they're pretty much the same thing. As theta approaches 0, and you should convince yourself of this, it's a standard topic, a standard demonstration in pre-calculus based on the unit circle definition of the sine, that for small delta theta, sine of delta theta is approximately equal to delta theta. Now I'm not going to take the time and distract for this, but you really want to understand why this is true. Certainly you want to understand that it's true because it's an approximation that we use a lot. But you want to understand why it's true. Okay, so dig that out if you need to. Okay, so anyhow, now we have an approximation to the area. So if we want to find the area between two values of theta, we can divide this region up into a bunch of small increments, add up the areas for all the small increments, take a limit, and we're going to end up integrating 1/2 r squared of theta d theta from your first theta to your last theta, whatever this theta is to whatever this theta is. Okay, well that's how you do area in polar coordinates. How do you do arc length? Well, we're going to move on to arc length, but I'll do that in a separate video.